Uh, so today our speaker, first of all, welcome everyone to our Soil, Water and Climate seminar. This is our 5th seminar of the series. And today our speaker is Dr. Isaya Kisekka. He is an associate professor of agricultural water management and irrigation engineering at the University of California, Davis. His research mainly focuses on irrigation optimization for enhanced crop production, economic and environmental outcomes. He also studies large-scale environmental impacts of agricultural water use on groundwater quality and quantity. So please join me in welcoming Isaya. And thank you so much for presenting on our series. Welcome. Floor is yours. Yeah.
Thank you, Vasu. Let me start my timer here. The title of my talk is Sustaining Agriculture in California Through Innovations at the Groundwater Irrigation Nexus. Broadly, as Vasu indicated, my work covers two interrelated areas, smart irrigation and agrohydrology. In smart irrigation, we are focused on finding or improving water management in specialty crops. We work in almonds, walnuts, processing tomatoes. And on the hydrology side, we are interested in understanding hydrologic processes that impact nitrate movement to groundwater, salt balances in agriculture-dominated watersheds. Very quickly about California agriculture. California is the largest agriculture state in the country in terms of farm and ranch cash receipts. It's valued at over $50 billion. Here, this graphic shows the top 5 states, including Minnesota. The top commodities are listed here. Dairy, which of course requires a lot of alfalfa, is the #1 commodity, followed by almonds and grapes. In this talk, I will talk mostly about almonds because they are the largest irrigated crop in California with over 1.5 million acres. And as a result, they use a lot of water. There are 2 factors that make California ideal for specialty crop production. One is climate, and the other is an elaborate water delivery infrastructure. In terms of climate, we have a Mediterranean climate in the Central Valley here that allows us to grow crops like almonds. 99% of all almonds in the US, 99% of all walnuts. And we also have a coastal climate here that allows you to grow leafy vegetables almost year-round. So as a result, California produces over 95% of all broccoli and over 92% of strawberries. And in addition, you have desert climates down here in Imperial Valley, as well as intermountain climates here close to the Oregon border. So this unique climate, especially the Mediterranean climate where you don't have any rainfall or almost negligible rainfall during the summer months and rainfall in the winter months, really allows you to grow excellent crops. The other issue, as I mentioned, is this elaborate water infrastructure that moves water from the north to the south where the demand is higher. It involves 2 major projects. One is the federal project, and the other is the state water projects, but they all involve a series of reservoirs that store water and canals and aqueducts that deliver water to irrigation districts that distribute the water to the growers. And in addition to these 2 major water delivery projects, you also have smaller local water delivery projects. In terms of irrigation systems, there's been an evolution in types of systems that growers use in California. Over the last 30 years, we've seen an increase in adoption of micro-irrigation and a decrease in gravity irrigation. In the 70s, gravity irrigation was the dominant irrigation method in California. But as there's been a shift from field crops, a lot of fields that were under cotton, for example, have been converted into orchards, almonds or pistachio or walnut orchards. And when they do that, the irrigation methods they typically install are either drip or micro sprinklers. And there's also been a lot of incentives, both from a federal level through the EQIP program or the state level through the SWIP program, where growers can get up to $100,000 to retrofit their irrigation systems. But going forward, I think the thing that is going to drive what technologies growers adopt or management practices they adopt is policies, specifically groundwater policies. So I'll talk about a few that directly impact irrigated agriculture. And the first one is known as the Sustainable Groundwater Management Act. This was passed in 2012 in the middle of the recent drought. In California, water swings between two extremes. You have historical droughts here I show in blue, and then you have historic droughts. The challenge is to manage both these extremes. So typically when you're in a drought, growers go to groundwater as an insurance policy to substitute for reduced surface water deliveries. And because of that, a lot of groundwater basins here in the Central Valley became overdrafted. And the state had to do something because you had started seeing subsidence and roads and water delivery infrastructure sinking. And so something had to change. And these groundwater basins that were created as part of SGMA are being categorized as either critically overdrafted, high priority, medium, or low priority, meaning they have to submit to the state groundwater sustainability plans that show how they are going to keep their aquifer sustainable. And on the other extreme is these floods. And most of these groundwater basins, which are in the Central Valley, where most of the agriculture is in the state, I've proposed to use what is called agricultural managed aquifer recharge, whereby if you have a flood event, you distribute this water on agricultural fields and you let it drain it into groundwater as a way to increase groundwater supply. Now, in terms of groundwater supply, this is a promising management practice, but there are concerns in terms of groundwater quality, because if you move this water through the vero zone, you're going to mobilize nitrates and arsenic and other contaminants that some of them are naturally occurring in the soil profile. Another policy that growers have to comply with is the Irrigated Lands Regulatory Program. This map here on the left shows nitrate concentrations in groundwater. And the red here are concentrations that are over 10 milligrams per liter. This is the EPA limit. If you drink water that has more than 10 milligrams per liter, it will interfere with oxygen movement in your body. It can actually be fatal for children. So a lot of communities, there are a lot of disadvantaged communities here in the Central Valley that have lost safe drinking water access due to groundwater contamination of nitrates. So the state has passed two laws. One is the Irrigated Lands Regulatory Program, and the other is a salt and nitrate program that I'll talk about shortly, which regulate discharge of nitrates to groundwater. So growers organize themselves in organizations called coalitions, whereby the state issues a discharge order to discharge nitrates to, for example, this Irrigated Lands Program, and then the growers have to work under the Irrigated Lands Program through their coalitions to comply with the requirements in the discharge permit. And so these growers are always on the hunt for management practices that would allow them to remain compliant, as well as remain to maintain their production. As you can see, farming in California is overly regulated. So the most recent one, which was passed in January of this year, is the Salt and Nitrate Program, which regulates, again, nitrates at a basin level, whereby these groundwater basins that are marked in red are being classified as priority 1 and the ones in orange as priority 2. Those that are under priority 1 have already received the notices to comply with this order, which means they have to report each season how much nitrates they have applied, how much was removed by the crop, and what is their potential, or what was potentially leached to groundwater. And this law now expands not only to irrigators, but also dairies, ranchers, food processors, wineries, and municipalities. So there are two pathways for compliance. You can go in as an individual, or you can go in as a management zone. This picture here depicts a management zone which would involve different entities that are regulated working together to demonstrate to the state that they are minimizing nitrate to groundwater, and they also have the capacity to provide safe drinking water in case they are identified as being non-compliant. The SALT program is under the Salt and Nitrate Management Program, but it has been deferred, and nitrate has been prioritized in terms of implementation of this policy. But in some ways, this is a more devastating problem because a lot of soils in the Central Valley are impaired by salinity. And with groundwater, as the aquifers get depleted, there's also concentration of salts. So most of the water now that we're getting is higher in salts than it used to be. And you can see here what can happen. You have these salt rings forming around your drip lines and actually killing trees. There's a study that showed that in the entire Central Valley, over 250,000 acres have already been taken out of production. 1.5 million acres are salinity impaired, and this problem, if not addressed, would cost the state about 1.5 billion per year by 2030. So it's a major problem. Next, I would like to briefly go over some of the projects that my research group has been working on to address the problem of demand, as well as groundwater quality. So as I said, I'm going to focus on almonds because they are the largest irrigated crop and tend to use the largest amount of water as a result. So in California, there's this organization called the Almond Board that advocates for almond growers, and they have what they call the 2025 sustainability goals. And their number one goal is to reduce the amount of water required to grow a pound of almonds by 20% by the year 2025. And to do this, their growers are going to need to refine their management practices and also adapt technologies that would help them achieve this goal. So one of the things we are looking at is to understand how much water young almond orchards use. And if we can refine the management practices, for example, can we manage the orchards by variety instead of managing them all as a single variety? And what are some of the promising soil and plant water status sensing technologies? The reason we are interested in understanding crop water use of young almond orchards is there's a rapid increase in conversion from field crops to permanent crops. For example, over the last 10 years alone, the number of non-bearing or young almond orchards has ballooned to over 350,000 acres. And the only way to irrigate these young almonds orchards efficiently is to understand how much water they use as they grow through their life cycle. We were fortunate to find a grower that had planted 3 orchards adjacent to each other at different times. So we had a first year orchard, second year, third year orchard at the same location that allowed us to quantify the water use simultaneously. So in each of these orchards, we installed a flux tower to basically help us quantify these components of the energy balance. So we had a net radiometer here to measure the net radiation, a sonic anemometer to measure the sensible heat flux, and we had a soil heat flux here in the soil. And we estimated latent heat, or ET, as a residual of the energy balance. So this is water use of a second leaf orchard. The spikes are due to irrigation events. If you compare this to a third leaf orchard, you can see that the third leaf orchard uses slightly more water, especially during the mid of the season, compared to the second leaf orchard. If you compare this with the fourth leaf orchard, in the mid of the season, it uses slightly more water than the third leaf, but not by much. If you compare all of them together, what we found was that most of the increase in water use is between second and third leaf. Beyond that, the tree is more or less stable in how much water it uses, because the canopy has more or less fully developed. And on the right here, we estimate cumulative water use from full bloom to give you an indicator of how much water to plan for a given age of an orchard. So for example, if you're looking at a third leaf orchard, you need about 850 millimeters. If you're looking at a fourth to fifth leaf orchard, or fourth year to fifth year, you're looking at over maybe 1,100 millimeters. To generalize that information, we had to estimate crop coefficients. These are usually estimated as a ratio of actual crop water use, or ETC, over reference evapotranspiration, theoretically expressed like this. And we generalize that information on crop water use by age by generating these crop coefficient curves. So if you have a 1 year orchard, your crop coefficient is approximately 0.4. If you have a 3 year orchard, you use a crop coefficient of about 0.9. And once you reach 4th year, your crop coefficient is close to 1. Okay. And to further generalize this, you could express this in terms of light interception, or fractional photosynthetic active radiation, which is a function of the canopy size. Again, to allow this information to be more transferable. The other project we are working on is to understand how to irrigate trees by variety, because an almond orchard is designed to have several varieties. For example, in this picture, these are my colleagues, and this is Kelly, the grad student working on this project. You need to have different varieties in order to achieve effective pollination. So in this picture, you see this variety is still in bloom. It has a white leaves, yet the next variety here, this row, is already past bloom, and it's already put on green leaves. This means these trees have different phenology. And the traditional method is to irrigate all the orchard the same way. But we wanted to investigate if we irrigated these trees differently, if there was a significant difference in yield and water use. So we had a 5-acre orchard that we worked in. We had a base station here in the farm shed, and we had solenoid valves here on each row. Each row here is a different variety. And then we developed a simple program that would allow us to open and close these valves remotely. The grower is located about 45 minutes drive north of Davis. So we didn't want to drive there every time we wanted to turn a valve on and off. So we were able to remotely turn on these valves and also record how much water we were applying. This picture describes how we implemented the irrigation. I added this picture here to explain an important growth stage during the life cycle of an almond is what we call hull split, or where the hull splits from the shell of the nut. When the crop reaches this stage, you need to deficit irrigate for two reasons. One, to minimize disease, or they call it hull rot, and two, to make the harvesting more efficient. The way almonds are harvested is by shaking, applying vibrations to the tree. When you deficit irrigate around hull split, you make the harvesting more efficient. So the traditional way is to deficit irrigate when almonds reach the hull split period, and all the varieties in the orchard to receive less water. But the new approach we were testing is to deficit irrigate whenever each variety. We had 3 varieties in this orchard. We had the non-parallel, which is the most popular variety. And then we had 2 pollinators, Aldrich and Butte. And in the first treatment, we deficit irrigated when we reached non-parallel hull split. And in the second approach, we deficit irrigated when each of these varieties reached their respective hull splits. And then we also varied the deficit irrigated levels. We had 75 as well as 50. And these are the results from the 2019 season. We did not observe a significant difference in yield between these different strategies, okay? As you can see here. However, there was a significant difference in variety, which is not surprising because this is already known that these different varieties have significant differences in yield. What we were interested in specifically is to see if we would observe a significant difference between these irrigation management strategies, which we did not in 2019. Similarly, in 2020, we did not see a significant difference in how you irrigated, whether by varietal or using the traditional method based on the non-parallel approach. So what this means is that it's maybe not worth the investment in terms of infrastructure to retrofit your irrigation system to have different valves on each variety, because the differences in yield were not significant. I'd like to briefly talk about some of the soil and plant water sensing technologies that we have been evaluating to help growers refine their irrigation management. Specifically, we've been looking at proximal soil sensing using cosmic ray neutron probe, as well as automated microtensiometers. Why these 2 technologies? Measuring soil water in tree crops is very challenging because they have these extensive routing systems where you put a soil moisture sensor can involve a lot of guesswork. So we wanted to experiment with a technology that gives us an aerial average. The cosmic ray neutron probe gives you an aerial average soil moisture at a shallow depth. And with regards to tree water status, a tree water status is a very good indicator because it tells you, it integrates all the responses from the diverse routing system. However, the traditional method that has been used is to use a pressure bomb, a pressure chamber to measure stem water potential, where you go at solar noon, put a foil around the leaf, let it equilibrate, and then go and cut it off and measure stem water potential. That method is very laborious, and growers were hesitant in terms of adoption. So they needed something that is more automated besides water, another limiting factor in California is labor. So it's not easy to find somebody to go around with a pressure chamber measuring tree water status. And so the idea was to develop these microchips. So what these are is you have a sensor, if you can think about it as a tensiometer, you have a semi-permeable membrane and you have water. So when the tree is water stressed, water moves across this semi-permeable membrane and there is a pressure difference that is recorded by the sensor. And when you irrigate and the tree is not stressed, water moves in the opposite direction and you record a signal, and then that signal is calibrated to estimate in form of a stem water potential. So these are our results. We had these sensors embedded in several tree trunks. And once they are calibrated, they give very good agreement between this traditional method. This is Kelly, my PhD student, working on this. You have to spend hours in the field between 1 and 4 p.m. at solar noon to get these leaves and measure stem water potential. So we think that having these sensors that could automatically give you similar information will improve adoption and improve water use in almonds. If they're not calibrated, they can be off, but once you calibrate them with a stem water potential, then they give you very accurate readings. Quantitatively, here the one-to-one lines, we saw R squareds between 0.7 to over 0.9 and root mean square errors that were as low as 1 to about 3 or just over 3. Okay, and so the question becomes, if you have this sensor embedded in a tree, how representative is it for the entire orchard? One of the things we've been working on is upscaling these measurements using machine learning, or specifically artificial neural networks. Can we train a model that can help us scale these measurements up? If we can provide soil information, vapor pressure deficit as inputs to the neural network. And the results are promising here. This is a training data set. We got an R of 0.87, validation of 0.88, and testing of 0.85. These are R, but if you look at R squared, they're a little lower, 0.76, 0.88, 0.73. We think this can be improved if we can provide better explanatory variables or more explanatory variables to the artificial neural network. The other technology we've been looking at is remote sensing of ET. Remote sensing of ET has been around for a long time. And in California specifically, it works well because we don't have cloud cover that affects a lot of other regions during the growing season. For example, this is at one of our sites. You can see the spatial variability. This is walnuts and this block is almonds. You can see spatial variability in crop water use. So if you irrigated the entire orchard the same way, some areas are going to get a little more water, others are going to get slightly less water. And we are validating these remote sensing approaches using eddy covariance. I think this technology has moved from research and it's now in the private sector. There are a couple of companies that are providing this as a service to growers. One is Irriwatch, another one is Gen Irrigation. They can provide each grower their farm-specific actual ET for each block. We compared that to eddy covariance and we see good agreement. We didn't have data here in the mid of the summer because we had wildfires that affected our infrared gas analyzer here, but caused it to have very low signal strength. So we removed those data points out. But if you look here where we had data from all systems and at the end of the season here, we see very good agreements, both from the commercially provided services like IRRIWatch, as well as other surface energy balance models like metric, SIBO, and the two-source energy balance approach. In terms of cosmic ray, our preliminary results also seem very interesting. The blue curve here is the cosmic ray. The cosmic ray basically measures, it senses neutrons, neutron intensity. So when these cosmic rays reach the surface of the Earth, they are attenuated by hydrogen. And the thing that has the most hydrogen near the land surface is water. So the more water molecules you have, the more attenuation you will have in the cosmic ray. And that will be associated with the neutron intensity above the land surface. And that is what this helium detector detects. So you can see here that the cosmic ray neutron probe is in agreement with in situ neutron probe. The in situ neutron probe is the one we take in the field and put inside access tubes to measure soil water. You can see good agreement here during the season, in the middle of the season, before you start to dry down the orchard. The brown curve here is remotely sensed soil moisture in the 1 meter root zone. As you know, for the in situ neutron probe, you can get readings at various depths. So red is 0.75 or 0.76 centimeters. Yellow is 45 centimeters, and the black as the near surface. Now, this is quite revealing because during the harvesting period, the neutron probe and the cosmic ray switched. Previously here where the profile is wet, the cosmic ray was in agreement with the 75 centimeter depth neutron probe reading. But at dry down, it's closer to the 45 centimeter reading, and somewhere between the 75 and the 20 centimeter reading. Because at this time, as I said, you're stressing the orchard, you're drying it down, you're preparing it for harvest. And then you harvest and shake the nuts, which cover the orchard floor for about 2 weeks, which the cosmic ray seems to be detecting that. Whereas the remote sensing based approaches were not able to detect that. Another interesting thing about almonds is as soon as you harvest them, you have to irrigate. We call that post-irrigation, post-harvest irrigation, because the buds for the next season are set immediately after harvest. Okay. Now, I'd like to change gears a bit and talk about nitrate leaching to groundwater from irrigated lands, and share 2 projects that we've been working on. One is looking at nitrate leaching to groundwater from irrigated processing tomatoes. We have a grower that accepted to work with us, and we started this project in 2019. We went in after the tomato crop and took soil cores up to 35 feet using a geoprobe, as shown here, at different locations within this field. The idea is we want to compare the mass balance approach, the Vedor zone monitoring approach, and the groundwater monitoring approach, because compliance to the policies that I described earlier are looking at these 2 approaches as a way to regulate growers. Currently, this is the only method that is being used, where growers have to submit their nitrogen reports, then the nitrogen reports have to show how much nitrogen was applied, how much yield, or which is associated to how much nitrogen was removed, and what could potentially have been reached to groundwater. This one, the Vedor zone monitoring approach, we're experimenting with, what we plan to experiment with what we are calling a deep Vedor zone monitoring system, where you have suction cups that are attached to a sleeve that goes all the way from the root zone to the groundwater, basically to understand how nitrates move from the time they are applied to the time they reach groundwater. Most of the work in the past has focused on monitoring nitrates either in the root zone or just below the root zone. Because of COVID, we had a delay and we did not complete installation of the deep weather zone monitoring system. However, we were able to complete installation of the groundwater observation wells. So we have 11 wells installed around the field. And this is the general direction of groundwater flow. We could not put any wells inside, would have loved to, but they would be in the way of the growers' operations. There is a lot of heterogeneity in terms of soil texture. Close to the soil surface, the soil type is basically clay. As you go deeper in the soil profile, the soil texture changes to sand and loamy sand. This graph shows nitrate concentration at different depth in the soil profile. We monitored this up to about 12 meters. The red line is nitrate concentration just after harvest of processing tomatoes. So the grower followed processing tomatoes with triticale. So we went back in June of the following year, the grower harvested triticale, and then immediately in July, we went back and did nitrate measurements in the same locations. And you can see that there's a lot of heterogeneity here in the measurement, mostly because of differences in soil texture as you go across the field. There was a lot of nitrate removal in the top, approximately 4 meters, but very little change here in terms of nitrates below 4 meters. Groundwater concentration was about 20 milligrams per liter. We have a similar project in almonds looking at nitrate concentration, and here we are assessing the impact of low concentration, high frequency fertigation on nitrate leaching to groundwater. We have groundwater observation wells here in blue and weather zone monitoring sites in orange. These are basically suction lysimeters with installed alongside tensiometers. So the grower here who is working with us, this project is actually led by my colleague, Thomas Hatter. The grower is implementing these advanced fertigation practices. What I mean by high frequency, low concentration fertigation, the grower makes frequent fertigation applications that are low concentration. The opposite management practice will be making fewer fertigation practices that have high concentration of nitrate. Irrigation is by ET. And this is how the weather zone monitoring is done. You have the tensiometers here up to 3 meters. You have a neutron probe access tube, and then you have the suction lysimeters. And there was a colleague that was also interested in nitrous oxide emissions, but these were low in terms of the nitrogen balance. And we're also monitoring nitrates in groundwater, as well as nitrate in the tissue in the almond nuts. What we have found is that high frequency fertigation did not affect yield, but improved nitrogen use efficiency. Heterogeneity is an important factor in assessing nitrate leaching. As you can see here, this is an interpolation of nitrate concentrations in the suction cups, and you can see that it varies very much across the field. And this is due to heterogeneity in the soil texture. These are our estimates for the mass balance approach. Leaching to groundwater was 6 to 28 pounds per year of nitrates. Root zone varied between the root zone monitoring based on suction cups varied between 25 to 150 pounds per acre. And if you monitored in groundwater, the leaching was about 20 milligrams per liter. Okay. And just to summarize, I covered an overview of irrigated agriculture in California, groundwater policies that impact irrigated agriculture in California, selected smart irrigation projects, as well as selected projects on groundwater nitrate leaching. I would like to acknowledge all my lab members, as well as my other research groups that I collaborate with. And thank you very much. I welcome any questions.
Thank you so much, Isaya. We open the floor for questions. Any questions? You can unmute yourself and type your question in the chat as well. We'll be monitoring that.
I've got a quick question. Satish, do you have a question? Or, no?
You go ahead and then I'll have a question.
I was just, thanks for the seminar. Isaya, it was really interesting. Just have a question about, I'm more into the nutrient management end of things. Can you give us an idea of how much nitrogen is applied to almonds versus tomatoes, and how growers, you know, whether they follow those recommendations or are they regulated to apply a certain amount?
They are regulated through the Irrigated Lands Program. Tomatoes apply up between 80 to 120 pounds per acre. And almonds apply on average about 120 to 150 pounds per acre.
Wow,
that is usually also influenced by the yield potential of a given block. So yields vary widely between the north part of the valley to the southern part. In the northern part of the valley, average yields are about 2,000 to 3,000 or 2,700 pounds per acre. And down in the San Joaquin and Turale Lake Benson, yields go up to about 4,000. So they tend to apply slightly more N down there.
So they base the rate on how much is being removed by the crop? Is that how it works there?
Yes.
Okay, thank you.
They also do tissue tests during the season, basically to guide them on how much to apply through their fertigation.
So can they apply more if a tissue test indicates a need, or
yes,
they have a limit?
No, they don't have a limit. They can apply more. However, they have to, with the new regulations now, they have to report how much they applied and how much was removed.
I see. Interesting. Thank you.
You're welcome.
Hi, this is Satish Gupta. Two questions. One is more of a general nature. Sometimes you get a almond which are bitter, and I was wondering what's the reason. The second question I have is about the suction cup lysimeters. That's such an old technology, and you get so much variation as your data shows. Have you ever tried other kind of technology like pan and wick lysimeter? I know we even over the year use suction cup lysimeter, and you get as you showed, pretty high loads that are going into the groundwater, but that's not the case.
Right. Yeah, that has been challenging. The wick lysimeters, they have been tried in other crops. One of their challenges is to really manage the suction within the wick, to make sure that the suction in the wick is representative to the suction outside the wick.
But you still have a much larger area to cover, and with the variability you are showing, you need probably hundreds of suction cup lysimeter. They are mostly useless.
Yes, that's true. Especially in soils that are very variable, you get a very wide range in data. Your uncertainty is quite large.
You got
Drainage lysimeters too are being applied, but they are quite expensive to deploy at a large scale.
you got any information on why the almonds are bitter?
That is usually associated with variety. So they're actually classes depending on how much you pay. For example, the non-pearl variety tests much better. They have almost a vanilla test. And those are usually packaged for various markets. And there are some that are only made for milk or other products. The test is really a function of variety.
Thank you.
So I have a question, Isaya. Thank you for your seminar. The question I have is related to the new regulation. I'm just interested to know a little bit more about how the regulators go about making sure that there is compliance, and if you have any thoughts in terms of the level of compliance that is happening.
So for example, SGMA, the law that regulates how much water can be pumped, establishes what are called groundwater sustainability agencies. These are local agencies where stakeholders come together and produce what is called a groundwater sustainability plan that they submit to the state. And in the sustainability plan, there are 6 things. They call them the SGMA sins. Thou shall not have groundwater overdraft. Thou shall not have subsidence. Thou shall not have, say, groundwater quality. If these things happen, then you'll find you're in violation. And then the state can come over and take over management of that groundwater basin. So as long as you show through groundwater wells data that you're in compliance, I think the state is trying to leave most of the management at the local level.
Are there concerns with, we know that water moves from the point that it, enters, or the nitrates, and where they end up. Are there problems? I mean, I actually don't know how big the farms are, but if the farms are not too big, is there concern that, a neighboring farm may be the one that is impacting your well, and you end up having to, pay for that or be regulated because of somebody else's problems?
Yes, that is true. And water may not respect boundaries, and some of the nitrates you measure, for example, below a given orchard may be coming from upstream from a dairy. And that's why the new law, the nitrate and the salt and nitrate program, is encouraging people in a given area to form management zones, which are a collection of different entities to be regulated together instead of an individual.
Thank you.
Yeah.
Hello, Isaya. This is David Mulla.
Hi, David.
I'm glad to meet you.
Yeah,
I think you've worked a lot with my colleague Prasanna Gowda in the past, and
yes.
I know that you've done some great work in the past with him. I had a question about the large numbers of nitrates that are leaching to groundwater. It just seems that no matter what you do in terms of best management, you still have very high leaching rates. Mm-hmm. And I'm just wondering if you have to look beyond nitrogen and water management to other strategies. I know you briefly mentioned growing a crop after harvest, I noticed the bare soil between all the rows and was wondering if there's any thought about growing cover crops or something else in those areas between the trees as maybe one other strategy that could be used to reduce the leaching.
Yeah, that's a very good question, David. Actually, it's cover crops are being encouraged. Growers could actually get incentives through the Climate Smart Agriculture Program to grow cover crops because they have a lot, they could help with nitrogen removal, but they also create habitats for bees that improve pollination and so on. It seems growers in the northern part of the valley are more receptive to the practice than in the southern part because it's so dry. It's to grow cover crops, they'll have to irrigate them, and so they have to make a decision on where to put the water, whether to put it on the cover crops or wait and put it on the crops. But that's a very promising practice.
And related to the bare soil between the trees, I've done some work with ET estimation in orchards using satellite imagery.
Mm-hmm.
And one of the things we notice is that the averaging of remote sensing data from the canopies to the bare soil creates errors in estimating evapotranspiration. And I noticed your ET estimates from metric were quite a bit lower than CBOL.
Mm-hmm.
And I guess I was just wondering if some of those differences have to do with difficulty of estimating, the ET from the bare soil versus the canopy.
Yeah, that is always a challenge with a cross resolution with a 30-meter pixel. One of the things the company that is providing the CBOL-based approach, which is IRIWatch, they do what is called thermal sharpening. They take the Landsat 30-meter resolution thermal data and sharpen it with Sentinel data. So you get ET at 10-meter resolution instead of 30-meter. That has tended to be slightly better than the Landsat 30-meter pixel resolution. As you said, you're averaging a bare area with a tree, and so that is bound to create uncertainty. Other people are using drones, but drones are harder to scale in terms of frequency and how much area, but they give you a much better resolution.
Thanks.
We have two questions in the chat. The first one is from Brandy. What are the factors contributing to the huge increase in almond demand in the last several years? Is it only almond milk or other factors?
I think it's the growth of the middle class in the Far East. I think a lot of our almonds are exported. But in the United States, there's also people's dietary preferences continue to change. And almonds are used in very, very many products besides eating them as nuts. There's almond flour. The hulls are used as livestock feed, almond milk. The shells are also used in cosmetics. So they have a variety of uses.
And the second question is from Louis Allen. What were the soils and parent materials you were working in?
The soils tend to vary, but most of the soils in the valley are alluvial soils. So in the northern part, we're working with predominantly clay soils. In the southern parts, they tend to be sandier soils.
Okay. I have a question regarding the ED estimations. Isaiah, you showed one flux tower with that yellow tower. Do you have any details about that we can use for what sensors you used and what are the cost of those sensors?
So we use a LICO covariance flux tower, and the two main components on that flux tower is the infrared gas analyzer. I think with an educational discount, it's about $18,000. So it gives you both CO2 and H2O, so you can do things like CO2 and water, so you get water use efficiency. And then the sonic anemometer is, I believe, about $4,000 to give you the three-dimensional wind speeds. And of course, there's a data log as an but those are smaller.
Is it the same? I know you showed eddy covariance system at the end, but there was one with the yellow frame. Was that eddy covariance as well?
No, that is called a surface renewal. That's very cheap.
That's what I was.
That's about $5,000. It does not directly measure ET like the eddy covariance, but you can get latent heat at a much lower cost. It's basically a net radiometer, a sonic, and thermocouples.
Okay. And my second question, that would be my last question about the cosmic ray sensors. I know you're doing this research, do you recommend them over neutron probe because they cover a larger area and also goes up to 2 to 3 feet for irrigation management?
We just started working with them 2 years ago. We've seen some advantages in the sense that the traditional neutron probe, you need a permit. They are regulated. The cosmic ray sensors, besides soil moisture, we can also use them to estimate biomass. Okay. Which we can use to estimate yield potential, but the cost is still very high. It's not affordable for a grower. Okay. But it has potential.
It has potential. Okay. Thank you. Any other questions from audience?
I do have one more question, Isaya. You have a lot of data now. Do you plan to use any of these data sets for either stochastic modeling, which you have a lot of experience in, or some kind of deterministic modeling?
Yeah, I would actually welcome any collaboration if somebody has more quantitative skills than I have, but some of my grad students are in the stages of writing up some of the data, but there's no reason why that data cannot be analyzed in a different way.
All right, thanks.
You're welcome.
All right, we are almost at 4:30, so let's all thank Dr. Isaya Kisekka for this great presentation. Yeah, you can use these, emoticons here. Thanks, Isaya. I know irrigation is not very widespread in Minnesota, but I think the water quality and quantity issues are same everywhere. And through your presentation today, we have learned a lot. Yeah, thank you so much.
I know Taylor, she didn't say something, but she worked with me.
Yeah, Taylor is from California, yep.
Hi, Taylor.
Hi, it's good to see you again.
Good to see you.
Yeah.
Are you enjoying Minnesota?
So far, even though there's snow outside, but it's okay.
She was one of the best in my classes. So.
Oh, goodness. Well, he was on my thesis committee, so I figured I'd better come by and at least listen to your talk.
Yeah, she joined at the time when everything went off like online, so we haven't got a chance to meet her in person, but I'm working with her on various research projects now.
Yeah, you'll be very pleased to have her.
Oh, thank you.
Yep.
Okay. Thank you, everybody. Bye.
Yeah,
See ya.
thank you, Isaya. Yeah,
Thanks a
thank you,
lot.
everyone. Last information about the second last seminar. So our next seminar is December 2nd. Dr. John Belota from Water Resources Center will be presenting on December 2nd. So see you all then.